today's portion basically I am taking from Raj Jain's book. So you can make a note of it, and if you want you can just go ahead and his presentation slides are also available. So if you want you can take a look at those also. This is something that I have made with some notes and some other references. And I hope that in the last class I had asked you all to go through certain distributions. So I hope that you all have gone through certain distributions because these will be necessary for this part of the course. All right. So let me start with today's topic, that is queuing theory. So when I was talking about it in the last class, I talked about certain situations, certain cases where you know you have a lot of people waiting for some job to be done. Okay, for example, I gave the example of collecting boarding passes from the airplane. Sorry, from the in the airport from the counters, and standing in a bank in a line for getting your job done by the person who's doing some cash job or something like that, whatever you want to do at the bank, and standing in a queue in your mess to have food. Okay, and it'll depend on the person who is giving the food, what is the speed with which he's giving the food, and how many people are actually standing in the queue. These things will determine that how much time a person will take to average time a person will take to get the food. Hmm. So this is how we generally see a queuing system. Okay, this is a just an overview, a third person view you can call it. Okay, so today we are going to do more uh, internal view of this system, and we will see that how it works out. So okay, there have been certain mistakes in the spelling of queuing theory in this. Okay, so it is QUEUEING. Okay, this spelling is the correct spelling. Okay, so please remember that and work accordingly. Okay, if I have done any mistakes here, so pardon me for that, and please consider it as that spelling. Okay, now as an introduction, when I was talking about this, so basically, when we are talking about queuing systems, why do we need such systems? Okay, in our as a computer scientist, why would we need to study about queuing theory? Okay, so first example that might come to your mind is that you have already studied about routers and everything, so maybe you might be thinking from that perspective that yes, in the routers there are many packets which basically get they cannot get served or they cannot move out of the router faster because of we have already seen that the switch fabric may not be fast, the line cards may not be fast enough. Okay, and maybe the scheduler is scheduling in a different manner. All right, so these may be the reasons, or more so the traffic is actually congested. First is, if the traffic is congested, then only the queue will be made. Okay, and once that is done, after that you will have such issues related to the speed of the switch fabric, the line card capacity, etc. Those will determine that how long the packet has to wait until it goes out of that particular router. Okay, so that is one that you can think of from your whatever you have studied currently. Now on top of that, or in addition to that, if as a computer scientist you want to say that okay, is it only necessary in networks, that the answer would be no, because it is also necessary in all other domains of as a computer scientist. Okay, for example, there will be many jobs that will be sharing system resources. Okay, for example, your CPU is getting shared, disk space is getting shared, etc. Okay, so those systems, they will also there also be waiting there. Okay, so those systems, they can also be modeled with the help of queuing theory, and one can find out that what would be the average delay in those cases. So if you start doing research in any of these fields, whether it be computer architecture, computer network, or any of computer so-called systems area, you will actually find out that, queuing theory has a very large hand in the analysis of those systems. Okay. So that's basically the introduction of queuing theory. Now, why would we need queuing theory? Because it will help in determining, how much time that the job will spend on an average in the queue that you are analyzing currently. Okay, so when we use queuing theory, it will help in determining the time that the jobs will spend in various queues present in the system. So what is this? It says it is theory, but is it actually what it is exactly? What is queuing theory? So it is nothing but mathematical analysis of a system. Okay, why are we doing this, or what are we? What is our objective in doing this analysis? We have already found out the objective, that is, we want to determine that what would be the average time that the job will spend in the queue in servicing the process. Okay, so it is nothing but mathematical analysis of queues and waiting times in stochastic systems. Okay, I am assuming that you all are aware of what is a stochastic system. If not, please go through Rajan's book. I've already told you to go through it. The basics chapter with all probabilistic probability distributions, etc. So please go through that. Those are your basic mathematics. And I think stochastic systems also comes under that. So please, the definition you should know. All right. So we use such kind of systems to extensively analyze production and service processes that exhibit random variability in market demand and service times. Okay, that means there will be random variability in the arrival times and service times, and in such systems, such kind of mathematical analysis, that is, they are exhibiting random variability in their arrival times and service times. In such systems, you can use queuing theory to analyze the waiting times. Now, as you know that a queue will arise or a queue will be made if the service that one is doing is exceeding the capacity. The demand for the service is exceeding the capacity with which the service is being provided. For example, in a bank counter, a queue is always arising when the number of customers which are arriving is much larger than how fast the person in the counter is serving those people. Okay, so again, if you take the example of an airport, there also it will depend on how many people are actually arriving at the counter and how fast the people in the counter are serving these people. This will lead to creation of a queue. Now, okay. So most often this creation of queues is caused by random variation in service times and the times between customer arrivals. Okay, we'll see how it is happening. And if there is a long-term demand for a service and that is greater than the capacity of the queue, then the queue will be exploding. That means too much of people will be waiting in the queue and it will get out of its capacity. So sometimes if you go to your mess and you wait for, I think, dosa, yeah, when they are making dosa, then it is very long queue. Some students, they just feel that it is going to take like half an hour or so, so let's just move out of it, and the queue becomes too large. Okay, at least some 60-70 people are waiting. So these things do happen, all right, and they happen when the demand for service increases increases a lot more than what is the capacity of the service counter or the server. Now let's get to our networks. Okay, so when we are talking from the point of view of computer networks, as I just spoke about, we think that okay, we in networks, when we are talking about queues, because we have read already that there is a queuing delay that is associated, because when packets arrive, if there is a congestion and routers are unable to serve the packets as fast as they are arriving, then in that case there will be queues in the routers. Okay, so we know that apart from that, we have three different delays. That is, you have for every packet you do have these three delays, that is propagation delay, transmission delay, and computation or processing delay. And then we have our queuing delay. Okay, so let's see how a queue looks like. This I had given you a glimpse of it in the last class when I was showing you that this will be a waiting line in the queue, and this is the dispatch line, and this is the server which serves the jobs which are arriving. Okay, and then once the job is served at the server, then it will depart from the system. Okay, so let us assume that this is a system, that is starting from the buffer of this queue to the end of this server. This is a system. Okay, now there will be arrival of jobs in the system. Okay, so the arrival will happen with some rate. It is assumed here that lambda is that arrival rate. Okay, so jobs are arriving into this system with rate lambda, and you have jobs waiting in this queue. Okay, this is your buffer. All right, the jobs are waiting in this queue. Now they will have to wait for some time before they are served. That will depend on where is this job. That means how many people or how many jobs are there in front of this job in the queue which need to be served. This is assuming that the scheduling is FCFS. All right. So if you get confused anywhere, please you can ask me question. Um, so basically jobs are arriving, they need to wait in the queue until their turn comes to be dispatched. Okay, so W is considered that waiting items, number of items that are waiting in the queue, and TW is considered here as the amount of time that they need to wait. Okay, and then once the turn comes, or once the job that you're looking for that is at the head of the queue and it gets the chance to be dispatched, it gets dispatched. Now dispatching discipline means the scheduling discipline that you are talking about. So let us assume it is FCFS for now. It can be any other discipline also. Some kind of priority based discipline can be considered here. So it is getting scheduled to the server. Now server will serve or execute the job, right? So it will take some time. That time is known as TS. Okay, here the time is given as TS here. So TS is equal to service time, and rho is given as utilization. Okay, utilization of the server. That means how much of arrival rate is how much of arrival of jobs is happening. That means arrival rate divided by what is the rate at which the server can serve. Okay, that will be the utilization. Service utilization we also call it, and it is denoted by rho here. And once the server is serving, then after that the job is done, so it will depart from the system. So this is the line of departures. Okay, so I was talking about this, that this starting from the queue here till the server, this is an entire system. Okay, so once a job arrives into this system, we can also find out that how much time it will take to get out of this entire system. That means if this is a black box, you will see that somebody is arriving, they're waiting for some time, and then they are departing. So your job is that you will just find out that what is the average time for which your job has to wait in the system before it can get out of the system. Okay, so that time is here denoted as TQ. All right, and Q is denoted as the items that are there in this entire system. That means ones which are in the queue and which are being served by the server. Okay, so this is basically our queuing system. Okay, these are very important parameters of a queuing system. So please make a note of these. Now let me go to the next slide. Okay, so sometimes what we can do is we can view the network as a collection of queues. Okay, so here it has been considered that you can consider it as having FIFO data structures. But as I was mentioning you about that, it's not always FIFO. It can change. The scheduling can change depending upon what kind of priority you are giving. What is the QoS that you have promised to your customers? Okay, so we already know that queuing theory will provide probabilistic analysis of these queues. That means the queues that we are talking about in the network. Okay, so for example, some metrics that you can get is that what is the average length of the queue. Okay, what is the probability that the queue is at a certain length? That means what is the probability that there are some n number of customers in this queue. Okay, probability that a packet will be lost. Now when a packet will be lost, when the queue is either full or the waiting time is so much that the packet's lifetime, that is the threshold for which the packet will be alive, that goes off. Okay, so that is less than when the waiting time becomes more than the lifetime of the packet, then also a packet will be dropped because it is of no use anymore. All right, so these are the ways we know already that if there is queuing delay and the queuing delay increases a lot, then the packets are lost because of either that the lifetime of the application is reached and it is greater than the waiting time in the queue. That is one way of losing packet, and another is that your queue is full because of too much of arrival of packets happening in your system and the packet got lost. So these are the reasons here. These are the metrics that you can, these are some example metrics. You can still find out much more metrics than this. Now let us get to queuing notations. Okay, so what do we know until now? That the system is made up of the queue and the server. Okay, now there should be some more notations. So let us get to the example of the airport. Okay, boarding pass counter, or you can think of your mess food counters. Okay, there's not one counter there, there are many counters. Okay, similarly in the boarding pass counter also, same set of people are being served by many counters. Okay, this is for the same airline company. All right, so that means there are, so what is happening in the airport? Many people are arriving. Okay, out of them, some people are going to a particular airline company. That means, for example, let us talk about Indigo. Okay, so many people are arriving into the airport. Some will go to Airtel, some will go to some other system, sorry, not Airtel, Air Asia, some will go to some other company, airline. Okay, but we are talking about the ones which are interested in going to Indigo. So those which are interested in going into Indigo will actually form a queue in front of the the counters of Indigo Airlines. Okay, so in general what happens, there's only one queue and there are many counters, and one by one they call people to give them their boarding pass or take their luggage. Okay, so let us assume we are talking about this kind of a situation. So what do we need to specify when we are going to talk about such a system? So first we need to specify about the population size. That means the, excuse me, that means the customer population here. So out of this, some of these are going into this queue, right? So this is the population size that we need to talk about. Then, we need to specify when we are going to specify a queue. Then we need to specify what are the number of servers. Of course, this is very, very important. That means how many servers are serving your queue. Okay. So number of servers is important. Then what is the system capacity? We'll get to system capacity here. Then the arrival process. That means what is the way in which the customers are actually arriving into the queue. Okay, and this way is not by walking or anything. Okay, please don't think like that. The arrival process basically means that what is the distribution that this arrival is following. Okay, arrival of the customers into the system. Okay, so that is what is important here. Then what is the service time distribution? Okay, that means how the service, how much service time is being required for each of these jobs that are arriving into the queue. Okay, so what is how the server is serving the jobs, that will be determined by the service time distribution. Then what is the service discipline? That is the scheduling that I was talking about. That means whether jobs are, or whether customers are served as first come first serve basis, or some other kind of uh, scheduling discipline. Okay, so these are required for representing a queue. All right, so here the definition of this queuing notations has been given. So first is population size, as was given there. So population size, as I mentioned, that these are the potential customers who can enter your system. So I told you that there are a large number of people which arrive in the airport. So those will be our potential customers who can enter your system. Okay. Now, most real systems consider this population size as finite. Okay, but when we are looking for an analysis, when we are doing a mathematical analysis, it becomes easier to assume certain values as infinite. Okay, so here too, when we are doing a queuing analysis, most of the times, for just the purpose of analysis, this population size is considered to be infinite. Okay. Then comes the number of servers. So as I already told you, number of servers can be either one or more than one, depending upon what kind of system you are looking at. Okay. Now, of course, when we do mathematical analysis, we do some loose assumptions. Okay, so the loose assumption is that these servers are mostly considered to be identical. But in real life, if you see, the way one person does a job is different than that of another person, whether it be in different counters of anywhere. Okay, one person can do a job faster, another person can do a job less faster than the person, or basically slow. So that is not a very realistic assumption, but yes, for ease of analysis, we generally take some assumptions. So one of the assumptions that we will be taking is that the servers are identical. Okay, now if they are not identical, suppose you still want to consider a system where the servers are actually totally different from each other, but there are multiple servers in the system. So what you do is you just start considering those servers with their queues separately. Okay, so you just consider that those are different queues altogether, and you can find out the values separately for those different queues. Okay, so this is for the number of servers. Then comes the system capacity. So in layman's terms, system capacity means how much your system can actually hold. Okay, so that means the number of jobs, or number of people, or number of packets, whatever you are considering. So the number of jobs that can wait in the queue in your system plus the one that is getting served. Okay, assuming that there is only one server. If there are multiple servers, that means the number of jobs that are waiting in the queue plus the number of jobs that are getting served, that will consist of the system capacity. Okay, so if you want to say in other words, then it will be the maximum number of customers that can stay in your system, including those which are currently waiting in the service and those which are receiving the service from the servers. Okay, now here to the queue length. Okay, in realistic systems, we know that queue length cannot be infinite. It has to be a finite length queue. Okay, but for analysis, we sometimes consider it as infinite length queue. Okay, so we will see that how what is the difference, how the analysis is done when you have finite capacity, when you have infinite capacity. We will see how things change in due course. Now let us have some variables denoting these processes. Okay, so first is the arrival process. Okay, so we are talking about that the jobs will arrive into your system from a given population size. So here that population size is given as customer population, and with some distribution they are entering into your system. Following some distribution, they are entering into your system, and that is known as your arrival process. Okay, so here an example has been given that there are students who are arriving into a computer lab, and there are many computers that will serve these that these students will use to do their work. Okay, so students arrive at different time instances, that is they arrive at times T1, T2, TJ and so on. Okay, and the inter-arrival times between these is given by tau j, that is equal to tj minus 1. Okay, now this this distribution that we are talking about is the distribution of these inter-arrival times. Okay, now we assume these as independent and identically distributed. Okay, and most commonly when we are talking about this inter-arrival time distributions, we consider them as exponentially distributed. Okay, so we assume that arrivals are Poisson, but they are IID, and their inter-arrival times are IID and exponentially distributed. And we know that this is the PDF of exponential distribution given by f of x is equal to lambda e power minus lambda x. Okay, please go through these distributions, the properties of these distributions. These will be very important. In which situation can we consider something as exponentially distributed? In which situation, of course, we know that there is a difference between them, that is discrete time and continuous time distributions. But still, what are the other properties? What is the PMF of it? So please go ahead and check these out. Okay, all right, otherwise it will be difficult for you to make numeric or just write down the numerical answers or calculate things. So it will be difficult, and for understanding further analysis also it will be difficult. If you have not done this, please do that. Again, I'm telling. All right, then next is your service time distribution. So what is it? So it is the amount of time that each customer spends at the server to be served, right? So again, it is usually considered to be as IID, and then most common distribution that is assumed for this is also known as is also an exponential distribution. Okay, so the service time distribution is also most commonly considered as exponential distribution. It can also be considered any other distribution. Okay, so this is for service time distribution, and then finally we get to the service discipline. So as I already mentioned, it is the order in which the customers are dispatched for servicing. Okay, so the scheduling order basically, so most commonly FCFS is used. Any other scheduling discipline can also be used depending upon what is the QoS that you have promised to your customers. Now let's get to the notation. How do we represent or how do we write a queue? Okay, so a queue is written with the help of this notation that is given to you. This one in bold. Okay, using slash. Okay, this notation is known as Kendall notation. Okay, so each one of these parts in this notation, okay, they represent something of the queue or queuing system. Okay, so what do they represent? So let's talk about the first value here, that is A. Okay, so A will represent that what is the arrival time distribution into the system, queuing system. Then S will determine that what is the service time distribution. M determines what is the number of servers in this queuing system. B determines that actually it will not be the number of buffers. Okay, it will be the entire capacity of the system. That means the um, number of jobs that are waiting in the queue plus the one that is being served. Okay, so that will be B. Then K will determine that what is the population size. We have already seen that population size is in general assumed to be infinite. And then finally the service discipline. In general, the service discipline is considered to be FCFS. It can be anything else also, and with that the analysis will change. Okay, now how do we represent these? Okay, arrival time distribution, service time distribution, etc. A and S do not represent any distribution. Okay, so some very common distributions are given like this. So first is M. Okay, some typical distributions that are used to represent arrival and service time distributions. So M is representing exponential distribution here. Okay, why it is M? Because it holds the memoryless property. Okay, does anyone know about the memoryless property? Because I had told everybody to study about exponential and Poisson distributions and many other distributions. Yes, please, if you know the memory about the memoryless property, can you please tell us?
I know the formula. Uh, Probability of x greater than s plus t and probability of x greater than s, then it will be considered as probability of x plus t only. Then we
It,
will take
I couldn't get you. What did you say? Probability of S. Can you repeat once again?
probability of that is x greater than s plus t
Ah,
and x greater than s,
uh,
then we will take x greater than s plus t only. We will emit the second thing, ma'am.
what do you understand by what you said? What do you understand by this?
And we will take the maximum thing, ma'am.
Maximum thing.
Yes, ma'am.
What is S plus T representing?
I studied in mathematics, ma'am,
Yes,
not
this
in
is
this.
mathematics only. I know, but that's what I'm saying. It is a property, no?
Yes,
Memorylessness is a
yes,
property.
ma'am.
So that is why I'm saying that it is mathematics only what I'm trying to teach you guys right now. Okay, so if you know the property, you can just simply say that this is the property.
I know this much only, ma'am.
Oh, you know this much only.
Yes, ma'am.
All right, some more thought should be given in this one. Okay, it is not like this happens or that happens like that. It's not like that. It has some meaning in that. Okay, somebody else, does anybody else know about memoryless property? Okay, so I had given this to you as a homework. I had asked you all to read about distributions, and it seems that nobody has done that. So I will not go through memorylessness now. I will wait for you for tomorrow until tomorrow's class to see these distributions and to look at the memoryless property. okay, which will be given in these distributions. Okay, so go ahead, check it out. Tomorrow again I will ask the same question. All right, and then we will see that what is memorylessness and the representation that what is your name, please? Can you please tell your name? You told about the memoryless property.
Vasant, ma'am.
Vasant.
Yes, ma'am.
Okay, so Vasant told about just one representation of memoryless property. I think there will be some yeah, some more it needs a little more thought on what you said. Okay,
Yes, ma'am.
so why it is that? Okay, it is a property. What kind of system follows those kind of properties? What is that property? Okay, what does it mean when you are saying some you said x greater than s plus t, right? Probability of x greater than x plus t, s plus t, right? You said that, right?
Yes, ma'am.
Yeah. So what does each of these value mean? Okay, what is it representing? So just mugging it up will not help out. We have to understand what is it. So this understanding needs to be there. Okay, you will get this when you go through the properties of these distributions. Please go through Rajan's book once again. I'm telling. Now, then we have deterministic distributions, where you know that you know how the or your time is specific, that you know exactly after this much amount of time there will be an arrival, or exactly this much amount of time will be taken for servicing a particular packet. So those kind of distributions are represented as D. Okay, deterministic distributions. Any other distribution that you know you are unable to put it into any category as such, then you put it under general distribution or G. Okay, so these arrival and service time distributions can be considered as M, D, G, and even some other kind of distributions like Erlang when we consider it as E with some K value. So if you see later on when we go for queuing distributions, you will find out that there are many ways of such representations. These are the ones which are most commonly used. Okay. Now let's get to different variables for all queues, and please remember these variables. I'll use this throughout. Okay. So tau is inter-arrival time. Okay. So that means, you know, from the customer population, your job is arriving into your system, or your students are arriving into your system. So that inter-arrival time is given as tau. Okay, so that is why in this time span it is given here that you know previous arrival and this arrival, that in between that time is given as tau. Okay, so we have represented the mean arrival rate as lambda. Okay, and that will be, how will we find that out? That is equal to 1 by e of tau. Okay, the expected value of tau. So this is 1 by e of tau. Now, this can sometimes depend upon the jobs in the system. Okay. Now, then we have S, which is the service time per job. Okay. And mu, which is the mean service rate per server. Okay. So these are different servers where each student will go and do his or her task. So mu is the mean service rate per server, and S is the service time per job. Okay, per job that the student is coming with to the server. Okay, so this is that. Then we have n subscript q, nq, which is the number of jobs that are waiting in the queue. That means here how many students are waiting in the queue for before they can get served by these servers. Then ns is the number of jobs that are receiving the service. So at this point of time, you can see that 2 students are receiving the service. Okay. Now, n will be definitely the total number of jobs that are in the system, that is the ones that are in the queue plus the ones that are being served by the servers. So, n is equal to nq plus ns. R is the response time. So, you have a job that enters into the system, and until when it can finish its execution. Okay. So R will be the response time and W will be the waiting time. Okay, waiting time is here. Until how much time does it wait in the queue? Okay, so please note that all these terms except mu and lambda are random here. Then let's get to the next one. So we have seen that how do we represent different values of or how do we notify different properties of the queue. Now we need to find out that what are the different rules that are required for queues. Okay, so we will have 4 different rules. So rules for all queues. Let us start with the first one, that is the stability condition. Okay, so first is that if your number of jobs becomes unstable, becomes infinite, that means at any time your server can actually not serve it in a finite amount of time, right? So your system will become unstable. Okay, so we need to, in order to analyze some system, we need to find its stability condition, right? So well, first we need to know that okay, this system is stable, then we will or the system has a stability condition, and then we will analyze this system, right? So for stability of a queue, okay, what is the condition that is needed? That means that is lambda should be less than m mu. Okay, what is lambda? We know that it is the arrival rate. Mu, we know it is the service rate, and m, we know it is the number of servers in the system. Okay, so what is the condition? That means lambda, that means the mean arrival rate must be less than the mean service rate. Okay, so this is the stability condition. Now this does not apply to finite queue or finite population systems, because finite populations cannot have infinite queues, and finite queues drop the packets if too many packets arrive. Okay, so therefore they do not have any infinite queue in their systems. Okay, but stability condition in general for queue is lambda should be less than m mu. Now let's get to the next part, that is this is basic, that is the number of jobs in the system, and there is a relation between the number of jobs in the system and the number of jobs in the queue. So we all have seen also right now that the total number of jobs in the system will be equal to the total number of jobs that are there in the queue plus the total number of jobs that are being served currently. Okay, so that is n is equal to nq plus ns. So with which we can also write that the average number of jobs which are waiting in the system is equal to the average number of jobs which are waiting in the queue plus the average number of jobs which are being served or which are currently in service. So this is written by this term, and from there we can also write that variance of n is equal to variance of nq plus variance of ns. Okay, so then last point is that service rate of servers service rate of servers independent of is independent of jobs that are there in the queue. Okay, so this is also a property of the queue, that the service rate of servers does not change just for the analysis purpose and all that. So the service rate of servers in the queue does not change with how many number of jobs are actually waiting in the queue. It is fixed, right? It will be fixed as to how the server can service, and it will also, it will depend upon how much big the job is for the customers that it is serving for. Okay, but the capacity of that server will be the same, right? For example, you go to the let us just talk about the airline example only. So you go to any of the counters, the person can serve up to his capacity only, cannot serve more than that, right? And but you will be waiting for what reason? Because too many people are there in front of you, too many people are coming into the queue, and the persons who are ahead of you, how much time they are taking for putting their luggage into the belt, getting the boarding pass, or they are having some other feud with the people. So all those factors will determine that how much time you will have to wait in the queue. Okay, so the service rate of servers is independent of the jobs that are there in the queue, and hence we can write that covariance of NQNS is equal to 0. Okay, now let's get to number of jobs versus the response time. So what is the relationship between that? Okay, so this relationship is given by a very important law but very easy law, and that is known as Little's law. Okay, so today I will just tell you what this law talks about, then we will talk about how to find this out or how to analyze, sorry, the proof of Little's law basically. All right, so if the jobs are not lost due to buffer overflow, then the mean jobs is related to the response time as this, that is mean jobs in the system is equal to arrival rate times mean response time. This is known as the Little's law. We can also use Little's law to find out, that is, what is the mean jobs in the queue. Okay, so mean number of jobs in the queue is equal to arrival rate times the mean waiting time in the queue. Okay, so these are known as the Little's law. We can find out different values using this Little's law, and when we are considering that we have finite buffers, then we use the effective arrival rates in place of arrival rate that is given in this equation for Little's law. So effective arrival rate essentially means that effectively how many packets are, or essentially how many packets are entering into your system after getting dropped out. So suppose you have the capacity to have 7 packets in your system. Okay, including the one that is in service. So assuming that you have only one server, so there's one guy in service and 6 guys that can be queued. Okay, so you are currently having some 5 guys in your queue which are waiting for service, so there's place for only one new guy. Okay, and if 3 packets arrive, so that means 2 packets will be dropped. Okay, so in general we consider that the queue size is infinite, as I told you, for analysis. So in that case you will simply find out that okay, whatever the packets are incoming, they can wait in the queue, so therefore you simply take the arrival rate for the calculations. Whereas when it comes to finite buffer sizes or finite queue sizes, in those cases you will take the effective arrival rate. That means effectively how many packets are actually able to enter in your system, and you ignore the packets which are getting dropped. Okay, we will see all of these. Okay, in further slides we will see that uh, during further analysis we will do analysis, a lot of analysis we will do in this chapter. So we will see with all of these cases how it works out. All right, so this is the last rule for queues, that is time in the system. What is the relationship between time in the system and the relationship between time spent in the queue for a job? Okay, so this is also pretty simple. The amount of time that is spent in the system by a job will be equal to the amount of time that it spends in the queue plus the time that it spends in getting served, that is R is equal to W plus S. So similarly we can write down like previously we have written that, so similarly we can write it down as E of R is equal to E of W plus E of S. We have also seen that service rate is independent of jobs in the queue. In those cases, you will have covariance of Ws is equal to 0, and with that variance of R is equal to variance of W plus variance of S. Okay. So this ends the rules for queues, Little's law and its analysis and everything. All those things we will do in the next class. Okay, because we are out of time today. Now, okay, so I will stop the recording also. If you have any questions, please go ahead and ask.